Hey there, and welcome. Today, we're going to solve a chemical mystery that's probably sitting in your kitchen cabinet right now. We're going to explore a really clever technique that lets us measure something we can't even see, and it all comes down to a single, critical drop of liquid. So, let's dive in.
It all kicks off with a pretty simple question. We all know vinegar, a key part of most salad dressings, is acidic. But how acidic is it really? Like, how can you figure out the exact amount of that tangy acetic acid floating around in a bottle of vinegar?
And that really gets to the heart of the problem here. The acid molecules are just dissolved in there. They're totally invisible. You can't just look at the bottle and count them up. So how do chemists do it? How do they measure something that's completely hidden in a solution? Well, the answer lies in some pretty cool fundamental chemistry.
To figure it out, we've got to look at this classic chemical duel, the relationship between acids and bases. You can kind of think of them as these two opposing forces that are always trying to find a perfect balance.
So what's the core difference? Well, it breaks down like this. Acids, like the citric acid in a lemon, have a whole lot of hydrogen ions floating around. That gives them a pH below 7. And bases, like what you'd find in soap, are pretty much the exact opposite. They've got a high concentration of hydroxide ions and a pH above 7. And it's this fundamental opposition, this kind of chemical tug of war, that we can actually use to our advantage.
So what happens when you actually mix an acid and a base? Something pretty amazing, actually. They neutralize each other. The hydrogen ions from the acid grab onto the hydroxide ions from the base, and together they just form simple, neutral water. This means we can use a base to perfectly cancel out an acid. And that is the key to unlocking our whole mystery.
All right, so there's this really elegant technique that uses this whole neutralization reaction with incredible precision, and it's called titration. This is the amazing tool that chemists use to finally solve our vinegar problem.
Now, before we see it in action, let's get the language down. Our mystery liquid, the vinegar, is called the analyte. That's the thing we don't know about. To measure it, we use a titrant. In our case, that's the base, and we know its concentration exactly. Now, the equivalence point is this perfect theoretical moment where the acid and base are in perfect balance. But you can't actually see that moment, right? So what we look for is something called the endpoint. That's our visible clue, the signal that tells us we've hit the mark.
So what does this actually look like? Well, think of it like a super precise science recipe. First, you carefully measure out your unknown stuff, the analyte. Then, you add a couple drops of a special ingredient called an indicator. And finally, drop by careful drop, you add your known solution, the titrant, until, bam, a sudden color change tells you to stop. But that, of course, leads to a pretty obvious question. Think about it for a second. Our vinegar is pretty much clear. The base we're adding is also clear. So, how in the world do you see the exact moment everything is perfectly balanced? This is where the real magic of titration comes in, right? How do we see it? When you're just looking at a clear liquid, what's the secret? What's the clue that tells us what's happening on an invisible molecular level?
Well, the secret ingredient is something called a pH indicator. These are amazing molecules that are basically like chemical chameleons. In an acidic solution, they look one way, one color, but in a basic solution, they look completely different. Basically, when the pH changes, the whole shape of the molecule shifts, and that changes the way it absorbs and reflects light. And that means the color we see changes.
And here it is. This is the big aha moment. This is a really common indicator called phenolphthalein. As you can see on the left, in our acidic vinegar, it's totally colorless. But the very second you add just enough base to neutralize all that acid, boom, the molecule flips into the shape you see on the right, and it turns this brilliant shade of pink. That flash of color is our stop sign. It tells us we're done.
Okay, so let's put all the pieces together and finally solve our salad dressing mystery. We've got all the tools we need, our acid, our base, and that awesome color-changing clue. So this molecule right here, this is acetic acid. It's the active ingredient in vinegar. And you see that one little hydrogen atom that's circled? That's the guy that makes it acidic. That is the invisible target we've been hunting for this whole time.
So, because we carefully measured every single drop of the base we added, we know the exact volume it took to turn the solution pink. And since we know the base's exact concentration, we can do a little math to figure out exactly how many base molecules we used. And here's the cool part. Because the reaction is basically a one-to-one deal, that number tells us exactly how many acid molecules were in our vinegar sample to begin with. Mystery solved.
Okay, so this is a cool lab trick. But why does it really matter? Does titration have any importance outside of finding out how tangy your salad is?
Oh yeah, it absolutely does. It turns out measuring and controlling acidity is critical just about everywhere.
I mean, the same ideas, this whole acid-base balance thing, they're happening all around us and inside us all the time. Your body, for instance, works tirelessly to keep your blood pH in this super narrow range just so you can stay alive. We use titration to check our environment for things like acid rain, to make sure our food is safe, and for manufacturing everything from life-saving drugs to cosmetics.
And this table, this really drives home just how precise and sensitive all of this chemistry is. Just look at this. A buffer solution that's supposed to be a perfect pH 7 at room temperature, well, it's not pH 7 anymore when it gets colder or warmer. It really shows you that in serious chemistry, every little thing matters. Even a few degrees of temperature can throw your results way off. And this quote from a technical paper really just says it all. It is absolutely imperative for all samples, when a pH value is reported, that the temperature at which the measurement is done is also reported. It's not just about getting a number, it's about knowing all the conditions so that number actually means something. That precision we saw in the lab, it's not optional, it's everything.
So when you think about it, we started with a bottle of vinegar, and we found that a simple color change, just a flash of pink, could reveal something totally invisible, the actual strength of an acid. It kind of makes you wonder, right? What other invisible forces, what other hidden properties are all around us, shaping our world, just waiting for the right clever trick to bring them into the light?